Hello all, welcome back to the part 7 of the Buffer Overflow Primer video series. Now in this video, we will look at a demonstration of the exploit me and hack you combination of programs. So let's now switch to our terminal. Let's open up the program hacku.c first. So what we've done is, in shellcode world, the smaller the shellcode, the better. So we've actually ripped one of the shellcodes from milworm.com. This is the URL. And this is a really small shellcode which does exactly the same thing which we accomplished, which the shellcode which we had looked at in part 5, and that is spawn a bash shell. Right, then we have defined a return address. Currently there is nothing here. We are going to fill this up a bit later. And then we have the main program. So what we are trying to do is create the egg environment variable, which we are going to go ahead and inject into the environment and later use as input to the exploit me program. So let's actually go back to our slides. And if you remember, as we said, the first 4 bytes, of course, need to be the environment variable name, right? So what we've done is we've defined a buffer of 96 bytes. And the logic is that 4 bytes for egg is equal to 24 bytes for our shell code, 60 bytes for some padding, 4 bytes for the pointer, and 4 bytes for the final null, right? So let's go ahead and look at how we are filling all of these parts up. So the first 4 bytes need to be filled with egg is equal to string. This is exactly what we are doing here, right? Before that, we've just gone ahead and set the entire buffer to the nope instruction, which is no operation. So whenever the processor hits a nope instruction, it just doesn't do anything. It's just like a wait instruction. Then we go ahead, copy egg is equal to onto the buffer, the beginning of the buffer, mind it. The next thing we need to do is copy our shell code, and this is where buffer plus 4, we go ahead and copy our 24 byte shell code. Then we do not care about these 60 bytes, and hence what we need to do is next fill up the return address, which would be at the 88th byte, right? So then we go ahead, copy the return address from the 88th byte to the next 4 bytes. And then finally fill the last 4 bytes with a null. Then we put the buffer onto the environment and go ahead and create a shell so that has the same environment variable set in it. Right. So right now the program has everything apart from the return address, because this is something we do not know currently as to where the shellcode is going to be in memory. So let's look at how we can figure that out. Let's go ahead first, compile the hacku program. So actually, let's first set a dummy value instead for the return address. Okay. Now let's go ahead and compile the program. Compile it. Now let's look at the exploit me .c program. So as we looked at in the slide, it's a very simple program, has a buffer of size 80 bytes, and then we have a simple string copy. Right, so let's compile this program as well. Great, both are compiled. So now let's go ahead and run the hacku program. So we have the shell, and This was expected. Let's look at if our environment variable has been set, which is the egg variable. So if you notice, the environment value is the value of egg is currently in the environment, right? Now let's go ahead and open up the victim in GDB. Open up the exploit me program in GDB. Right. Let's set a breakpoint for main. Let's now run the program, giving it the input of the environment variable egg, because this is what is now going to be passed as argv1 to the exploitme.c program. Okay, so we are here. The string copy is about to be executed, but before that, let's actually look at a couple of things. So if you remember from the slides, this is how the buffer for the program currently looks like. The stack for the program currently looks like. There are 80 bytes here of the buffer variable. Then we have 4 bytes of EBP and then 4 variables of the return value. Right, let's actually disassemble the main program. And if you notice, subtract 0x50, which is hex from ESP, means 80 bytes, which is the size of the buffer variable, right? You also pushed in EBP. So now let's look at exactly how does the return value on the stack currently look like. So let's do a bit of math. 80 bytes for the buffer, 4 bytes for EBP, and 4 bytes for return, which means a total of 88 bytes, right? Which means 22 words. So let's look at the top 22 words on the top of the stack ESP. Right? So these are the 22 words one after the other. So this, as we would expect, would be the return value on the stack. Verify that by going ahead and disassembling this memory location, and as expected, libc_start_main is available here. Okay, let's go back. So this is what we need to override with the pointer to our shellcode, right? Now let's look at how our shellcode is looking like in memory. It's at the argv1 variable, and if you notice, this is exactly our shellcode. And finally, we've currently set the return address to all A's. That is why this is what it is. Now when we execute the string copy instruction, this is going to be overwritten with this. Step through the program. We executed that. Let's look at the ESP once again. And if you notice, now this has been overwritten, right? So however, instead of this should actually point right now to the top of the buffer, or the beginning of the top of the stack, or beginning of the buffer variable, which is this address. So we need to replace the return address all A's by this specific address. So let's do that. Let's exit the program. And let's open up the HackQ program. So this point basically okay, now what we need to do is simply replace this with this value. Actually, this needs to be in reverse. So let's actually first write it down. Let's go ahead and remove this. So this is what our return address is going to be, right? Let's recompile the HackQ program. Let's run the HackQ program now. verify the environment variable has been set. It has. Now let's go ahead again, open up the exploit me program in GDB, break on main, and run with the environment variable as input. Now let's go ahead and look at the top of the stack. So this is the return address we need to overwrite. Let's look at argv1. This time, if you notice, argv1, the final return address, has been set to the top of the stack. And this is our entire shell code. Let's go ahead, step through this instruction. Now look at the stack once again. And if you notice, this time onward, the return address currently points to the start of the buffer variable on the stack, and that is where our shell code begins. Now, when we continue execution, what will happen is, once main returns, transfer will go here and our shell code will be executed. So if we continue, if you notice, let's continue. Executing new program bin/bash, right? And this is what happened, is basically that the bash shell was spawned. And if you notice right now inside GDB, the bash program which was invoked because of our shell code is currently running, right? So this is basically the point which I wanted to convey, is that once you overwrite the stack and place the correct return address on the stack which points back to your shell code, after that everything should be very simple. So, well, that's all for this video. Hope you enjoyed it. And in the next video, we will look at a much more advanced version of buffer overflow, where basically the stack will be non-executable. And we will look at how to go ahead and still compromise the system using the return to libc attack. So please leave behind your comments for this video. I would love to hear what you liked, disliked, and thank you for all the encouragement. That is what keeps me going and making all these videos. Thank you.